Okay, so hello everyone. Firstly, my name is Matheus Medeiros Silva, and postdoc at INF and PISA. And firstly, I would like to thank the organizers for giving me the opportunity of presenting my work on this amazing symposium. The title of my presentation will be Relativistic Effects on the Pass Light Cone, and is done in collaboration with Pierre Béchat, Giovanni Marozzi, Giuseppe Fanisa, and Tiziano Scavone. Okay, so nowadays we have a very good understanding on the composition of our universe. However, we still have some problems that we have to solve. And precision cosmology may be that it might open new prospects on having some advancing on solving these problems. And it means that for precision cosmology, not only we need accurate observations, but also accurate theoretical predictions. So to give accurate theoretical prediction, first we have to understand what we measure. So for instance, if we think about the luminous distance redshift relation, that gives us a very direct measurement of the expansion rate. The light that we receive to compute, for example, to obtain to evaluate the luminous distance redshift relation, reaches through our pass light cone. And due to the perturbation, and then we have perturbations on the pass light cone that may modify part of this information that reaches. So in order to fully account for these perturbative effects, one must to perform theoretical predictions that are in direct alignment with how observations are performed. And already in 2012, Ruth Durer and Camille Bonvin teach us that the observations are performed in our pass light cone, in the observed pass light cone with respect to the apparent angles of the position of the source, and then if we have a theoretical setup that gives us the cosmological observer directly in terms of these quantities, it might simplify a lot the task of computing these observables. So, okay, this talk will be mostly based on these works here, where we are developing the procedure to compute cosmological observables on the pass light cone in a very simple way. Okay, so the pioneering works, they usually what people do to compute, for example, the luminous distance redshift relation. So you solve perturbatively the geodesics equations. Then you have to solve perturbatively for instance, the Jacobi map. You use the Jacobi map to compute your observable. And then you express it in terms of your fiducial cosmology. So for instance, for the case of a luminous distance, you can express it in terms of the redshift, and you have the luminous distance redshift relation, which is a gauge invariant quantity, a very well-posed cosmological observable. Instead, I'm using this new approach called the Josi gauge that was introduced in 2030. It provides covariant expression for these cosmological observables in a very general way. So you have expressions for the angular distance, for the redshift, in a way that is independent of the geometry of your space-time. So for any geometry of your space-time, your expression is valid. So it changes the entries on the metric, and it will change the observable, of course. So we use this to perform perturbation theory directly on the pass light cone. So in this case, we just have to linearize the covariant expression, express it in terms of the fiducial model, and we will have the gauge invariant cosmological observable. So we do not need to go throughout all of the procedure, because in this case, the Jacobi map is solved non-perturbatively. Okay, so what's this Josi gauge? This Josi gauge is a gauge where it's already based on on things that we observe. So directly in terms, one of the coordinates is the pass light cone. The time as measured here, tau, is the one as seen by a free-falling observer. And the angles are already the apparent position of the source. So are directly the angles that we do measure. So when you choose this set of coordinates, you arrive to this metric that's valid for a genetic geometry of the space-time, where epsilon, you can see epsilon here. For instance, if you have freedom Lemaitre-Robinson-Walker background, this is just the scalar factor, or you can see also as the inverse of the redshift. And UA for freedom in this case, UA you can see just as a shift vector that will control the misalignment when you go from one path light cone to another. So how your angles have to change so that you still have the apparent position of the source. And for freedom, and this is just 0, but for Bianchi, you have something different, and also for freedom plus perturbations. The nice feature about this gauge is that because of the independence between these coordinates, you have the time-like geodesics in a very simple way. It's just a delta. The same for the photon for momenta. And because of these reasons, you can obtain the redshift and the angular distance in a very simple way, also with the observer terms, that Pierre will be talking more about it, about the observer terms. Okay. So the prescription of the observables in this scenario is very simple. Since we already have the nonlinear expression of this of the observables, we just have to express our observable in terms of our fiducial scenario. So, for instance, in the case of the luminous distance redshift relation, we just expand it around the observed redshift. Or there are other scenarios that people are considering now, like the cluster, the number counts in terms of the in luminous distance space. So your fiducial cosmology would be different, and then you do a different expansion in this case. But it's very simple, using this formalism. So then now you have a gauge invariant observable, and because you have a gauge invariant observable, you can just express it in whatever gauge that you want. So for instance, you can express it in terms of the Poisson gauge, and this will give you your result directly in terms of the Bardeen variables, the Bardeen potentials. So you do this by just performing a simple gauge transformation, order by order, at whichever order that you are interested on your cosmological observable. Okay. And then, yeah. So basically, these are the expression of the gauge modes. So when you compute your observable, it factorizes into just expression at the observer and that and just an expression at the observer and at the source. And instead, when you express it in terms of the Bardeen variables, then you will have all the integrated effects. So for instance, if you have a luminous distance redshift relation, you have the peculiar velocity effects, you have integrated and local Saxoff effect and Lenzing effects that appears in the expression of the gauge modes to fix this particular gauge choice. And once you express in terms of the redshift, then your gauge dependence that appears here in some of these terms, they go away, they cancel each other, and you have a gauge invariant quantity. So yeah, here is just explaining how to do this, how to go to redshift space. Yeah, this just expanded, since we have the expression of the redshift, is very simple to just expand it at a linear order and define this new parameter tau z that now will express our observable in terms of tau z, and then it will be gauge invariant. We are also building nonlinear relations between these between observables, so we can generalize also. This is completely general. You can generalize it to other cosmological observables. So, for instance, when you have a cosmological observable, in principle, you have 4 constraints on how to fix your coordinates. So you expand these constraints order by order, and you ask these constraints should be satisfied order by order. You solve and you see how your coordinates change in order to satisfy these constraints. So here we derive the nonlinear relation between the observables, in the case of the redshift. And I let you with my conclusions. For a neat description of the observer terms, please see the talk of Pierre. Thank you very much.